Okay. So the question is, okay, the same questions. Okay. Yeah, so let me review a little bit the questions. The first question is asking about the horizontal tangent, vertical tangent. Okay. And then the other one is asking about the concavity, where the curve is concave upwards or downwards. Okay. Now before we start doing the second derivative, let me just make some quick review. So we know that from our chain rule, we have these relations. Okay. Actually, we can write, maybe it will be more clear if I write like this. It's practically similar to what we have done in ddx, like this one. Right? Okay. So we are using the ddx as our tool to derive, right? Okay. Why I'm really emphasizing this structure, I will show you how to take on the second derivative. Okay. So the second derivative we will get on. Right? We can say that the second derivative is basically the derivative of dy dx, right? Okay, nothing wrong with this. Now, in parametric, the steps on how to write down the second derivatives is basically we are going to start in a structure. We need to do the same process with this one. Okay? So if we have ddx, like ddx, this one, of dy over dx, then we are exchange this y with dy over dx. Okay? So the second derivative gives us the structure okay. Why we need to do this step with the same structure as the first one? Because the first reason is we need to remember that our assumption in parametric is always that x is a function of our parameter t, y also the same, but y is also a function of x. Okay. So because y is also a function of x, we need to do this procedure slowly, okay? Not making a conclusion that is, for example, this is different with this. Okay, this is not the same. Okay, remember that in parametric, we are always stick on our chain rule connection, okay, which is from these terms, the chain rule connection. Okay, so because we have this connection, which is the dy over dt is equal to dy over dx multiplied with dx over dt. Okay. That is our chain rule connection. So this is our rule. Okay? Our rule. So when we have this, let me show you the beginning. Okay. When we have this, it seems that we just need to derive one time. Okay, we have the dy over dx. Maybe if you don't think clearly on the chain rule, you will go to these conclusions. Oh, it means that if we have second derivative dy over dx, we need to find the second derivative of this. Then we will have a second derivative of the parametric, second derivative of parametric. Okay? And that is not clearly the correct way. Okay? It seems that it's correct because you make some wrong conclusions from the first one here. This terms is actually, again, we are going back to our chain rule connections, which is stated that x and y is function of parameter t, but y itself is function of x. So it has a connection to this y and x have a connection. So that's why we have this chain rule connection. Okay? And that's why when we have the second derivative like this, we need to derive this as in the first way the y derived, which is we have d over dx and then dy over dx. Okay? And then if you look at how the structure is, it's simply the same as what we done here. dt, y, and then dx over dt. Because we have the same chain rule over and over, we just replace the y with dy over dx. And this is how you are getting the second derivative. Okay? I hope this is clear. Okay? I hope this is clear. So, if you have questions that ask about the second derivative, do not go to this route. Okay? It's not correct by definition. Okay? By definition of the chain rule. Okay? Okay. Okay, so we can go back to our example. Let me just maybe write one more time. What is the question? We just write the curve. If we have curve we can find the dy over dx. Okay, and then the questions, there is actually one question that haven't been mentioned. Show that curve has two tangents at 0.30. we look on the x and y, if we plug in 3 and 0, we need to find the variable t. Okay, so variable t at x equal 3, then we will have t squared is 3, so we have t equal square root of 3 and t equal negative square root of 3. So at this point, then we can find the tangent. Let me just write plus minus, okay? Just to note that I will calculate two of them. So dy dx, dy over dx, we will have the first one is a positive one, and the second one is this, right? You can calculate here. You can input plus minus square root of 3. So that's why we have this two slope for the equation of tangent line. And then based on the point, then we have y minus 0, x minus 3, and we will have two equations. I think I can write directly y. So this two equation we have. Let me copy this, all equations. Copy. Let me put here so that I can write the other one. Okay, just a quick review. Horizontal tangent. This is when the slope is 0, which means if we are converting it to parametric, this is 0, this is not 0. Then we get that the point is 3t squared minus 3 equals 0. So t squared is equal 1, or t is plus minus 1. And we can compute xy from this t plus minus 1. We have 2 points. And then the vertical tangent, that is actually when dy over dx is, let me just write infinity. T is equal 0, or we can write down the point is 0, 0, the xy point. Okay, now to find the concavity, we can check the second derivative. Let me write down the first derivative is 3t squared minus 3 over 2t. Okay. So this will be, this is 2t. This is 4t squared. So after some calculations, 12 minus 6, it's 60 squared plus 6. 4t squared divided by 2t. Okay, now we have this expressions. We have these fractions. Okay, now what we are going to do, we can set up line number, and we need to find or configure which interval that is having concave upwards and having concave downwards. Okay. If you look here, because of the squared, the quadratic, it means that they are a positive function. They are a positive function. And I think the one that makes the function seems important is just a 0. Oh, sorry, it's cube. Sorry, cube. So this one is a positive function. And this one is a cubic. That means it's determine positive or negative. Okay. So we can directly write down that 0 will be the important number, because when t is positive, it's positive. When t is negative, it will be negative. Okay. So we know that this will be positive and negative. When we have positive in second derivative, we know that this will be concave upwards. And if negative, it will be concave downwards. Okay, so quick review for second derivative. Okay, now from here we can draw the curve. I want to draw in here, but let me make it smaller. Okay, I think we can draw the curve. The vertical tangent will be here. This is 0, 0. This is 1, 2. This is 1, -2, the horizontal tangent. Maybe just slightly draw the tangent. And at the 3, 0, maybe here, this will be the, there are 2 tangents. Okay, so this is the thing. This is when t is equal -1. This is when t is equal 1, and this 1 is t equals 0. So it should be, okay, if we look on oh, by the way, this is t, okay? This is t, okay? Because sometimes we make some mixing up with the x and the original function and the parametric one. Okay? So this is already in parametric. Okay, so this should be t is, this is, I will just write this is t. Okay, this is t. So if this is t equals 0 here, then this is negative. It should be concave downwards based on our conclusion. So it should be going here. Okay? And this is the positive, right? T equal 1. So it should be going here. Okay. Okay. So this should be going there, and this should be going here. And then don't forget that in every parametric, you should draw the arrow indicating how the t will vary. Right? This is from -1. Actually, from this t, -square root of 3, right? This is -square root of 3. Let me draw here. This is t, and also t square root of 3 at the same value. So meaning that we start from this -square root of 3, start from here, go to -1, and then go to 0, and then go to 1, and go to square root of 3, the positive one. It's going to have the same point as the one at the beginning. Okay? That's how, at least we sketch the curve using the calculus, okay, in parametric. Okay, any questions first? Okay.
So this is x-axis.
Yeah, x and y. X and y. So in the parametric, we're still dealing with the Cartesian curve. X-axis, y-axis. Still doing this. But when we are dealing in the polar, in the next sections, we are not dealing with x, y, but we are dealing with the polar, the radius and the theta. Okay, but that's still later. Okay. Another example in your textbook, there are some example that is about the cycloid, but I will just give you the question and you try by yourself, because I will go to the next section on this parametric, which is the integrations. But let me give you just example on the questions, okay? And all the lectures are recorded, so you can check when you have some, maybe some confusions. You can check the video one more time. Okay, so the questions about the cycloid is suppose cycloid just a quick recap on how we are going to deal with the cycloids. Remember that this is your cycloid, maybe like that. Okay. So probably your horizontal will be here. Okay, you need to figure out this, right? And probably your vertical is probably around here, but I think the picture is not so clear that this is the cycloid. Should be having like a circle like that. More curvier in here. So you will see that this at this point, you will see at least it seems that it has some vertical. So to approach this, you can use the limit, either from left or right, on this theta here. Theta equals something. Not theta. It's this the distance. The distance. If this is 0, then this should be 2 pi r, 4 pi r, and etc. etc. You can try it using the limit. As theta is approaching 2 pi, let me just write n because it can be 4 and multiplication of that. So this is how you find the vertical on the cycloid, the vertical tangent. And the rest is actually the same as we done on the just a normal parametric, okay? So yeah, you can try by yourself for the cycloids. Okay. Okay. The next topic is the area under the curve. Let me write what we have done in calculus 1. This is pretty much the integrations that we have done in calculus 1. It should be positive. Okay, if we can make these functions here into a parametric, okay, we traced by parametric. Let's say we can have x as, let me just write the same terms. X is function of t and y also the same, different function. And we have alpha as our initial t, and beta as the terminal point. Okay, we can write first, we write the original functions like that. Okay, the idea is to keep the terms of the chain rule. Okay, remember the chain rule that we have is based on this chain rule. In derivative, in also in integral, we still keep the same terms. Okay, we keep the same terms, the same rules. Okay. The idea now, instead of taking the x as our integrations, we are going to change all terms with the parametric. So we are going to have not the x but dt. Okay. So the idea is, let me just write this as integrations. Let me just write dt first. Okay. Write dt first. Okay. And because y here is the function of x, but we want to change this y into a function of t. So let's just change to this g. Okay. Now what will happen with the dx here? We want to make it into dt. So we can write here dx over dt. So that the chain rule is still, we are using that to make out this area of the curve with the parameter. Okay. And then because all is, because we already make some assumption here that the curve that we have from A to B is actually can be traced out, can be tracked with the parametric from alpha to beta. Then this is also alpha to beta from here to here. Okay. Or we can take this as we can write with x prime t and then dt. It's this, yeah. Or maybe f prime, because that is our parametric one from here. But I think up until here, this should be you can see how the actors, how the pattern, how the formula looks. Okay. Now, let me give you some example on the cycloid. Okay. Let me draw this cycloid. Let's evaluate just this one area here. If this is start from 0 to 2 pi, let me just write 2 pi r. So from this 0 to 2 pi, area under the curve at the beginning, we can write, let me just write based on the general rule on area, so y dx. Okay. And in cycloid, we have connections for x and y that is function of theta. Okay, now to deal with this, we can take y and dx based on our parametric. Okay. So we can use our y here. But remember, this y is function of parametric. Okay. And we take out dx, so we need to derive one more time. And remember, the radius here is just a constant. Okay? It can be any number. Because it will be, remember that this is actually came out from you have a circle and you are circling the circle like maybe you rode a bicycle, and it will be impossible if the radius is changing, right? It will be, it's impossible. So radius is just a constant. You derive that, and you end with the derivative, and then adding the theta. Now, how about the endpoint here? Because we now observe the angle, then this should be the angle, which is from 0 to 2 pi, right? And its correspondence match the 0 and 2 pi r. So this will be r squared. Let me just factor out because of it's just a constant. Okay. Now we need to have some calculations. Let me just write really quick here, just to show you. Just a quick review. If you have this squared in a trigonometric, the best way to solve is you need to change the square into a double angle. Okay. What is the double angle? Double angle is, this is basically the basic one is from this cos squared minus sine squared, and you can have It depends on what you are squaring. You can have 2 cos squared theta minus 1 or 1 minus 2 sine squared theta. So you can exchange this with double angle, and then you can just integrating. And I think it's not too difficult to integrate that. So I will leave that to you, okay? And you can finally you can have the final answer for the area, okay? So that's the area. Let me put this into the right side so we can see clearly here. Okay, any questions? Any questions? Okay. And I think for all the techniques inside, they will be similar with this calculus 1. The only difference is if you change all the usually just y equal function of x, you change it to the parametric. So usually you end up with the dt or any variables that you decide on the parameter, maybe theta or t. These two variables is commonly shows up in the parametric. So well, it can be also another variable. Depends. Actually, it depends on your. The next part, aside from area, we have the arc length. The arc length. If you don't remember what arc length means, let me just draw a random graph. Let's say this is y equal a function of x. What arc length means is we have to measure how long is this function from, let's say, this point here to here, or maybe let's say we have the maybe from here A to B. How to evaluate this length? The idea is we are cut pieces by pieces of this whole function, and then we observe one small piece, maybe in the middle here, and then from there, let's say we have a tangent. Okay, so imagine that we have tangent on this point, right? Different tangent in different slope. Okay, so let's say we have one over there. And let's name this this tangent is dl. It has a certain value dl, and it has a two component. Okay, two components. Okay. So why we are using tangent? Because that's the best way to approach this line here. If you draw in the paper, or when you draw the curve and then draw the tangent, it seems that when you are looking from here, there's a gap, right? This gap here. And when you're going here, the gap seems gone, right? So that's why if we take this curve as small as possible, we can approximate with a small error that our tangent here is actually similar to our curve. That's why if we have a lot of small tangents that we can combine from A to B, the DL, and we can combine them with integral, then we can measure the arc length. Can you get the idea? Okay. And that's just my quick recap of arc length last time. In calculus 1, right? Okay. So how to deal with this, okay? For me, the best way to approach this is just using the Pythagorean. So doing this is, I think, very simple and very intuitive. Okay. Instead of taking pieces by pieces, using limit, Riemann sum, I think that takes too long to see. But if you just want to look intuitively, you can just looking on the Pythagorean theorem. Okay? It's a little bit different from your textbook, because your textbook it is going to have some proof with the Riemann sum, because that is officially the integral. But what I want you to look at is, you can just look on the Pythagorean. Okay? And then what we can do from here is we can take this square root. Okay, take this square root, and then we can take this in terms of okay. Let me just change this dy into dy over dx, multiplied by dx. It's actually the same thing, right? But we can factorize dx, right? We can factorize outside. And then we can have 1 plus dy over dx squared and then dx. Okay. Now, like I said before, because we already know the integral and we don't need to prove the integral one more time, right? We don't need to put the Riemann sum in the limit of the rectangle. Okay. We can just take the integral, both of this. Okay. Take integral. And let's say we have L. And now you have the arc length with the dx as the integration, or you can exchange with. Okay, so this is the arc length. Okay. We already learned arc length from calculus 1. But now, from this arc length, okay, we need to trace the function into the parametric. So let's just write, I think from here, okay. From this square root of, let me just write. dl is okay. Now we need to input our dt, and based on the chain rule we have, we can have this dx and dy. Okay. Let me just write the functions. Now we have dl and then dt, like that. And then we can have the arc length in total. Let's say we have alpha, beta. We can trace the functions from variable t from alpha to beta. Okay, in general, this is the formula, but there is some other assumptions that you need to think and be careful, okay, on this subject. Okay. Let me copy and take on the next page. Okay, from here. Okay. Okay. Let me give you the example first and see what do you think. What do you think about that? The first one is you have x is cos t and y is sine t. I think same example as the last Monday. I gave you that if we have this, then this will be a perfect circle, right? If we take out the arc length using the formula, this will be giving you sine squared t plus cos squared t, which is 1. So this will giving you 2 pi at the end, which is the circumference of the circle with radius 1. Okay. Okay, nothing really strange here. Nothing's weird. But if you have another example, okay, let me take all the derivatives from x and y. This will give you 2 cos 2 theta, right? And y prime will give you negative 2 sine 2 theta. And if you square this, this will give you 4 cosine squared 2 theta and also 4 sine squared 2 theta, right? And then we using the same formula. Let me just write directly the value. Okay. Now sine squared plus cos squared is 1, so you just square root of 4, which is 2, right? And then you write down this 4 pi. So what is wrong with this? Or what is unusual? First, both of this, like this first one, cos t sine t, cos 2t sine 2t, they both are circle, right? But in the parametric, if you have this 2t, remember that on Monday class, the first one is just a circle. This also a circle. But we are moving twice, right? So after we got 2 pi, we move one more time, so 4 pi. So that's why we get 4 pi. So we need to take one note here. We need to write one note, okay? that the arc length, if you want to measure the arc length, you know that it's just a circle. It should be how much? 2 pi, not 4 pi, right? Unless you are circling around, and because we just want to measure the arc length, only the shape itself. So we need to make one note that the movement of the particle should be only once. So they need to take these notes here. Let me just write as if curve C described by parametric, let me just write all the parametric. And then the T is from alpha to beta, F prime and G prime are continuous on alpha beta, and let me write with this C is traverse or move, okay, or move exactly once as T increases. And then we can write the formula
like suppose the like sin 3D, so it means the arc length is 6 pi. I mean, if the T is 3D sin 3D, so it means like the arc length would be 6
just
pi.
2 pi. We don't measure how long he runs. We measure only the distance. Okay? That's why we need to make sure that exactly once. So we remove any repetition. Okay?
What about if the radius is different? If the radius is different?
Yeah, that's a different case. Different case. This is the same circle. It's the same circle. Later also, but I think it's in a polar system. You will notice that if you have like maybe from 0 to maybe 2 pi or maybe pi or only pi, sometimes when you put on all the interval, you will get 0. But when you draw, you can draw. So it seems weird. But you need to make out, because it will be having a positive and negative value. So you need to maybe keep half and then multiply by 2. But it will be later on. Okay, some examples. So you can draw the parametric. When you use the formula, arc length is 0. Why? It's because it has positive and negative. But that will be a later case. Okay? Later cases. Okay, this is arc length. So it should not be equal 4 pi. Okay. Okay. Next cases or next section on the arc length is we have we call the arc length function. Okay, I think I can write the formulations first. That the ST is arc length along curve C from initial point to a point, let's say this is ft and gt on same curve C. So remember, arc length functions in calculus 1, we are just taking to x, right? From a constant to x. Okay. And then we usually use t. And we can relate also to fundamental theorem of calculus, right? But now, since we already established our arc length in parametric, then we can write the st. So from a constant to t, now we are using t, not x. So inside, we will use another variables, maybe u. So we are using du, not dt. So if we also remember, if s is a distance, like in physics, then we can have a velocity, which is the derivative of s. Then we can derive this integral, and we can use the fundamental theorem of calculus. Okay. So let's say we have v, that is the derivative of s. Okay. If we imagine this s and it's an physics cases in distance velocity, then we can have this exchanging u with t. I will write this. This is fundamental theorem of calculus. So arc length functions. And the last one will be the surface area. And that will be all on the calculus in parametric. Okay. So we can also imagine the arc length function as you have an initial point, and you can take on any other point, and you are mentioning as t, as a variable t. Okay, one more part on this calculus parametric is the surface area. I think I can write down the formulations for the original one first. That is in the calculus 1. So if you have this, just a random function, and you want to rotate in about the x-axis, then you will have this, right? We already established in calculus 1 how to find the surface area. The surface area is from the maybe let's just write s is integrations 2 pi y, and then this is ds. Let me just write ds. ds means the arc length. this is rotating about x-axis. If it is rotating about y-axis, then we have as 2 pi x ds. This is rotating about y-axis, and this is same the arc length. Okay. So basically, the arc length that you have, we can put into our equation here. So it can be in a dy dx, right? And this is still calculus 1. Now we are going to change this into the parametric one. So we just input the ds as in the parametric. So we change this ds with the parametric arc length, and that's it. But maybe let me write in complete. Suppose C is given by the parametric equations, and let's say we have alpha to beta for our t, and f prime, g prime, these both are continuous, and then our function g is a positive function. And we need to also make sure that curve C traverse exactly once. From alpha to beta. Then for rotation, if rotating about x-axis, then we can put into our formulations. Or you can write y as g of t, okay? And same thing, if you have the rotations about the y-axis, then you can write the 2 pi x, okay, instead of y. So you just extending the variable. It depends on the quantity, rotating about x-axis or y-axis. So later on, after we finish the chapter 10, I will give you some summary and some quick exercise, and also your TA also give you some exercise as well. But I would like to just finish on the important point on the calculus part in parametric, and then we can move to another subject, which is the polar coordinates. Okay. Polar coordinates. Okay, so polar coordinates. Let me start with this picture. So we call this horizontal line here is the polar axis. Okay. So first is we establish some rules on the polars. Okay. So let me just make it quick. We call this polar axis, and we measure the positions of P. So P can be in any different positions. It depends on the radius, okay, the radius of here, and the angle. So we can imagine this like a clock. Okay? But the positive angle will be counted when we are moving our hand or our clock counterclockwise. Okay? And we are moving. If we are moving clockwise, it will be a negative angle. Okay, that's just some rules. Okay. Okay. But the interesting part is, if we look on this coordinates, okay, we call this the polar coordinates. It's based on the radius and the angle, right, the theta. If we imagine we put on every possible positions of P, it seems that the radius is always positive, right? It's always positive. It seems. What is happen if this is negative? Okay. If you remember and if you have learned about the polar, if you have the negative, then it means that it is on the opposite side of that radius. Seems weird, right? Seems confusing. So let me draw here. If R is on this side, okay, then let me draw the other one. Let's say we call this as a negative R. Let's say this is negative R, and then theta, the same. So negative R is actually here. But in terms of what it looks like visually, the negative is gone. We cannot see the negative. Okay? What is really happening here is actually, this is the same way we say, this is actually the same R, but it's adding the pi. So this is in the visuals, this is R and theta plus pi. Okay. Okay, let me put you to some examples. Okay, if we have 2, 3 pi, which means this is radius, this is the theta. I think it's still easy, right? Which means that we are going to have 1.5 circle, right? 2 pi and then adding additional pi, right? And radius is 2. I think that's clear. How about we have 2 and then negative 2 pi over 3. We have the negative on the angle. Okay, like I said before, if we have negative on the angle, then let's say this is the polar axis. And we are going from this polar clockwise. So we are going here. And let's say this is negative 2 pi over 3, maybe around here. Or you can write this negative as in from here to here. Okay, we can also write that. 5 plus this is 1 over 3. So 5 plus 5 over 3, 4 over 3, 5. You can also write like that. Now, the problem that I mentioned, let's say negative 3 pi over 4. Let's start with the polar axis. Now where's the graph? That's negative 3. So, yes. Now let's just take it as in a positive way first. And let's assume this 3 over 4 pi will be around here. Okay? Maybe around here. Okay, let's just draw the 3 over 4 pi first. Okay, this is 3 over 4 pi. And let's just make this is the positive one first. Okay. The negative is, again, as in the opposite sides. Here. Or this actually 3, but it's plus pi, so it's 7 over 4 pi. Okay. So whenever you find negative, then it should be the opposite sign. Because we can find the negative as in the sine or cosine, there will be at least 1 and negative 1, right? So there will be a negative, right? But we need to convert the negative in terms of polar system. Then we need to comprehend that this will be the rules. Okay. And I think the other part, aside from how we draw or how we visually observe the position, is how to convert from Cartesian to polar and polar to Cartesian. Okay, let me move to another one. In Cartesian, we can take the polar into a triangle, right triangle definitions. Where x is r cosine theta, y is r sine theta, and tangent theta is y over x, and then we have a circle formula in Cartesians. Okay, this is just some ground rules, and we can see later how we are going to check our graphs, okay, in polar curves. Okay. And now the polar curves. The polar curves, this is basically, we are going to use the radius as a function of theta. Okay. Okay. Firstly, we introduce the simplest one. Okay. Let's say we have r equal 2. So if the statement saying that the equation is r equal 2, which means that it will have always radius 2. So the shape will be is a circle with a constant radius 2. Right? Okay. If we take the polar axis, and then let's imagine that we have several radius. Okay. R equal 1, R equal 2, R equal 3. And usually, if the Cartesian is based on rectangle, 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 this is how polar should be. Like if you know the, I think if you are still in elementary school, if you remember, there will like a book that is usually, sometimes some school they were using for drawing a graph, like a rectangle, rectangle. And then you can easily draw shapes, right? This is Cartesian. But in polar, the background is actually like this, like circle, circle, and circle. So you can draw some curves. If they change the radius, they maybe, okay, we change the radius, or maybe we take some loops here, or we make it into like a flower. Okay? So the background to help you to draw is actually using a circle with different radius to help you draw the polar curve. Okay? But this is just to show you how the polar system based on. Okay? So this is when we have the r equal 2. But when we have the angle is constant, let's say angle is maybe pi over 4. It will be, let's say we have pi over 4 here. There will be a line. Okay? It will be a line. One single line. Maybe here. Okay. These two examples are the simplest that we can imagine in the polar. Okay. Now the next one is r is equal to cosine theta. we can take this into a table value and check on the special angle, okay, from 0 to 2 pi, or maybe pi. I think it's just enough. Start from 0, pi over 6, pi over 4, pi over 3, pi over 2. This will be 2, right? This will be square root of 3. This will be square root of 2. This will be half, so it will be 1. This should be 0. And if you increase and check on the 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi, this will give you the negative of the same value, right? Okay. And now let's check on the drawing. Let me make a new one. This is a polar axis. Okay, let's start from theta equals 0. Okay, theta equals 0. So theta equals 0 is here. Theta equal pi over 2. Theta equal pi. 3 over 2 pi. This is theta equal pi. Okay, let's start with theta equals 0 is having 2. Maybe 2 is here. And then pi over 6. Pi over 6 may be around here. And the radius should be square root of 3. So if this is 2, maybe around here. Maybe there, or maybe a little bit here. This will be square root of 3 pi over 6. And then pi over 4. Maybe here. This will be square root of 2. And pi over 4. And then pi over 3, this will seem symmetrical with the pi over 6, right? And then this will be 1 and square root of pi over 3, sorry. And then at pi over 2, it will go into 0. And then we get into the negative. Negative 1 and 2 pi over 3. Two pi over 3 is going about here, right? But it's negative, so it should be going here. Okay? Get it now? So it's going back to here, around here. And notice that because it has the same value, right? And should be mirroring exactly the same positions. So it will be mirroring this and the other one here, here. And then if you connect all this point, we will have a circle. Well, my drawing seems a little bit off, but let me make it a little bit better. I'm taking this. It should be in a point here. Should be a perfect circle. Okay. So this is 2 cosine theta. And of course, the radius, if you see, the radius is changing, but this is a circle, not a perfect circle like the circle with radius 2. This is radius is 1, right? If you compute this exactly in the distance. If you want to convert and make sure that we are going to have the correct calculations, we can write down the formula in terms of so we have r squared is 2x, which means that 2x is x squared plus y squared, right? And we can take the standard formula for a circle from here. So this will be having 0, 1, 0, centered at 1, 0. Now it seems that it's perfectly aligned with our circle here. So if we change the background with the Cartesians, it's perfectly centered at 1, 0. If we change the background with the Cartesians. But remember, this is in a polar. Okay, this is 2 cosine theta. What's happened if we multiply with negative? It will be mirroring this, right? Okay, because all the value will be having opposite signs. So it will be having like this. That's the negative. What will happen if this I change 2 cosine theta with 2 sine theta? Positive 2 sine theta. If you draw and you check the value of the special angle, it will be going here. Perfectly up here. If you multiply with negative, it will be going here. Okay. And there's a pattern. In all the polar curves, not only the circle one. When you have the later on the Limason and etc., there will be a certain pattern. Okay.
Professor,
Yes.
what about tangent?
Tangent. What do you mean?
We have r equal to tangent or to tangent.
Yeah, but I think for tangent there is special cases because some of the points will be having infinite value. But we can make some limitations. Okay. Next part is actually about the Limason or cardioid. If you want, you can check 1 plus cos theta and 1 plus sine theta. You will notice that the pattern that I showed you before, the plus and the negative, will also be applied to this case. But try, maybe trace the curve, okay? Or even if you just log into some graphing calculators, you can check the graph. Okay, I think I will just end the class up until this introductions. Okay. We will continue on next Monday from this folder. Okay.